Hi, everyone. I'm going to be discussing the topic of cell metabolism. I'm going to start with carbohydrate metabolism. I'm going to get a pointer here. So I'm going to do this quickly. Okay, so yes, you can have a better understanding of what this is. Okay, so basically, what I want you to see, what you see here in this PowerPoint presentation or this Word document, you can see a table of all the terms that you're going to be learning throughout this presentation. Okay, at the end, you should be able to um, give a definition of all these terms at the end of the presentation. But I want to start by saying that cells need energy, and the energy that the cells use is in the form of ATP. ATP is a smaller energy currency that you can get from organic molecules like these macromolecules, like carbohydrates, lipids, or fats, or proteins. Proteins are our last resource. We don't want to use them first. But the most common resource that cells use is glucose, okay? But also we can break down fat and use fatty acids to make energy. Both require oxygen. If you want to maximize the amount of energy that you want to produce, you need oxygen. If you don't have oxygen, the cells are going to make a limited amount of ATP, and that's not going to be sufficient for their survival. Okay, so so we can also use specific amino acids to make energy as well. Okay, but again, amino acids are the building blocks of proteins. We want to leave proteins alone and use glucose instead. Okay, so why do cells need energy? Cells need energy for cell division, for protein synthesis, for muscle contraction, right? I mentioned this in the review. For transporting ions, remember that in AMP1, you learn about that we have active transport mechanisms that require energy, especially like the sodium-potassium pump, and that's needed to maintain the concentration gradients of sodium and potassium across the cell membrane, okay? So we need a pump because remember the laws of diffusion. Ions move from a higher concentration to a lower concentration. And we have specific channels for sodium and potassium that are always open. They're passive leaky channels or selective channels. And those are going to be always opened. And so we're going to have sodium always coming in because remember that sodium is highest in concentration outside of the cell. Inside the cell, cells have a lot of potassium. Okay, so cells are always losing potassium and are always gaining sodium. So these ions need to be pushed across, from low to high, and that is active transport, and that requires ATP. So sodium, the sodium potassium pump will pump out 3 sodium ions in exchange for 2 potassium ions. So you want to pump out sodium and you want to bring back potassium and reestablish their concentrations across the membrane. If ATP was not available, then these ion pumps will not work, and we will fall out of homeostasis. Okay, so the point of the story is that cells need ATP, and they need a lot of ATP, and this is important because especially if you have a stressful life, where cells are being damaged, there is from free radicals and things like that. And so we always need energy to stay healthy. Okay. So again, where do we get energy from? From organic molecules, especially glucose. Okay. So we're going to talk about how glucose is metabolized by a cell. Okay. So what is metabolism? Metabolism is the sum of all these reactions where things are being broken and other things are being formed. Okay, so when we build things, we call that anabolism. When we break things, we call that catabolism. All right. So again, we need to know why cells need energy. Okay, and and again, to run all those processes, all right? Now, there's a very cool analogy made by Professor Fink. This is a professor out of California, and he mentions that ATP are like the quarters that you use to run the machines at the laundromat. So basically you have a dollar bill and you put it into a machine. The machine gives you quarters, and then quarters are used to run the machine, like the cell. The machine will be the cell. And the washing machine, it will be the cell. But then the machine that does the exchange, from paper to quarters, that will be your organism. So basically, the dollar bill is like glucose, right? And then we're breaking it down into smaller units, which cells can use to run their processes, okay? So here I show you how ATP looks like. ATP is nothing more than adenine. Now, adenine is a nitrogenous base. Okay, adenine is, you have what is known as purines and pyrimidines bases in DNA and RNA, but adenine is one of the nitrogenous bases, and is notice that it's linked here with a pentose sugar, a sugar of 5 carbons. We call that ribose. Okay, when we put this together, this is called adenosine. And when we add phosphates here, we have adenosine monophosphate, adenosine diphosphate, adenosine triphosphate. So this is like a nucleotide. Nucleotide are the building blocks of nucleic acids, remember? So adenine it will be the nitrogenous base. Ribose will be the pentose sugar, and then a phosphate bond, so a phosphate. So this is like a nucleotide, okay, a high energy nucleotide. And that's why, when this is one of the reasons phosphate is important, is to build, high energy currencies like ATP. Okay, so phosphate is like an electrolyte, okay? So now to understand this process very well, we need to know the anatomy of the mitochondria, the structure. We need to study that, the structure of the mitochondria. Remember in AMP1 when they told you that, what is this organelle? And you said, this is the mitochondria. And what is its function? And you said, this is the powerhouse of the cell. Well, it is the powerhouse of the cell because this is where most of ATP is made, okay, in the presence of oxygen. Okay, so this is an organelle, okay? These are organelles within the cell. And notice that it has its own DNA, okay? So they think that this was something that was living on its own, and got into our cells, and they just, stay in the cell. So and then we have this symbiotic relationship where we both benefit, So anyway, so we need to know the structure, So I do this in AMP1. In AMP1, I talk about the structure of the mitochondria. Why? Because you need it for AMP2 to understand cell metabolism. Because otherwise, you're going to be so lost, in understanding this topic. Okay. So notice that this organelle, okay, this organelle has an outer membrane, okay, and it also has an inner membrane. So it's a double membranous organelle. In between these membranes, you have a space that's called the intermembrane space, okay? The space that you have in the inner membrane, after that inner membrane, that is called the matrix. That's called the mitochondrial matrix. And you can see that in the matrix, we have ribosomes, we have DNA. This is mitochondrial DNA. This is not nuclear DNA, okay? This DNA is used for the survival of this organelle, okay? Nuclear DNA is for the survival of the cell. But, if there is a mitochondrial disease, like anything that affects this DNA here, you have mutations, that might affect, your ability to produce ATP, okay? So these mitochondrial diseases that are very rare can result in low energy states, okay? Now, there is another protein embedded here in the inner membrane, which is called the ATP synthase. And you see it here. It has an FO portion and an F1 portion. The F1 portion is pointing into the matrix, so it's hydrophilic, it likes water. And the FO portion is embedded in the inner membrane and it's hydrophobic and it hates water. You don't need to know that, but this enzyme here, which is called ATP synthase, is important because it's the one that is going to be making ATP here in the inner mitochondrial membrane. So again, to recap, the mitochondria are, they used to be independent, organisms, and they got into our cells, and then we develop a symbiotic relationship, and we need them so that we can make a lot of energy so that the cells can do all these processes, okay? The important components here will be the outer membrane, the inner membrane, the intermembrane space, and the matrix. Okay, period. That's it. All right, now let's move on. Let's move on because we need to move quickly through here. All right, so I'm gonna my presentation here is gonna be highlight of this material. Okay, so you don't feel overwhelmed. Okay, this topic is all biochemistry. Now, you see that organic molecules like amino acids, which are the building blocks of proteins, lipids, and simple sugars like glucose can be used to make ATP. Notice that when a cell makes ATP in the mitochondrion, right, of the cell, notice that most of the energy is lost as heat. How much? 60%. 40% will be ATP, and it's going to be used for all these processes that I mentioned. Okay, so if you need to build something like protein synthesis, you need to have energy. You need to invest in energy. You need to have energy. Okay, let's move on. Let's get right into glycolysis here. Okay. By the way, 3 important things here. Glycogen is the most abundant storage form of carbohydrates. Glycogen is stored in lipids and they stored in muscle. Okay, glycogen can be broken down to make glucose when you are fasting. Okay, if you're fasting and you're not eating and your glucose levels are dropping, glycogen can be broken down to make glucose. And then that will stabilize your glucose levels once again. Triglycerides, remember that triglycerides these are the primary, this is the most abundant storage form of lipids. So we store lipids in adipose tissue in the form of triglycerides. If we need energy, like for example, when you're fasting as well, and when you run out of glycogen, for example, or glucose, when you run out of glucose, then you can use like triglycerides as well. You can use your energy. Like for example, when you run out of glucose, you can use your storage forms of energy, like glycogen and triglycerides. Both of these, if you want to make a lot of energy, you need oxygen. Now, so triglycerides are the most abundant storage forms of lipids. Okay, we can break down triglycerides into glycerol and fatty acids, and fatty acids can be used, can be further broken down into acetyl-CoA, and then we can use acetyl-CoA to make energy. Okay, but again, we need oxygen to be available. Proteins are the most abundant organic components in the body. They perform many vital cellular functions, including like enzymatic functions. We want to leave them alone, okay? We're going to leave them as the last resource, okay? So these are your best resources here. But I wanted to highlight specific things. For example, if they ask you, who is the most abundant, what is the most abundant storage form of carbohydrates? That will be glycogen. And what will be the most important energy source? That will be glucose. If they ask you most important storage form of lipids, that will be triglycerides. Okay, and if they ask you most abundant organic components in the body, you'll say proteins. Proteins are the most abundant organic components in your body. So let's move on. Let's move on. Okay, this is a reaction here that shows you, like in synthesis, in a summary, what happens when during carbohydrate metabolism. So we have here glucose, right? It's a 6-carbon sugar, right? So glucose is a hexose. We need oxygen, right? And we're going to form carbon dioxide. We're going to form water, and we're going to form ATP. And most of that energy is going to be lost as heat, right? So heat is going to go into our blood, and then it needs to be, and the body will cool off somehow. Okay, so notice that we're oxidizing glucose. Moving forward, we're oxidizing glucose. Okay, and we are reducing oxygen to water. So we're oxidizing glucose to carbon dioxide, and we are reducing oxygen to water. So you're going to have a better understanding of what this is, okay? I promise. All right, so let me continue. So glycolysis takes place in the cytoplasm of cells, and it does not require oxygen, so it's an anaerobic process. We call this anaerobic metabolism, okay? So no oxygen required. It occurs in the cytoplasm. What is glycolysis? Lysis means separation or breakdown of glucose. So we're breaking down glucose in the cytoplasm in the absence of oxygen. Okay. Now, aerobic metabolism, this requires oxygen, and it's also known as cellular respiration. This happens in the mitochondria. Okay. But first, we're going to talk about glycolysis, and then we're going to move on to the mitochondria. Okay. So let's continue here. By the way, one of the end products of glycolysis is pyruvic acid. Pyruvic acid, when you put it in water, in aqueous solution, then a hydrogen ion will come off, and then it's going to exist in this ionized form, and this is like a negative charge here, and we call this pyruvate. Okay, so that you understand that sometimes these words are used interchangeably. Okay, so if they say pyruvic acid, this is a non-ionized form of the molecule. But pyruvate will be the ionized form of the molecule, okay? Like if he's putting pyruvic acid in water, it's called pyruvate. And I like to use pyruvate, because I want to keep it real, all right? Now, there's some factors here that are needed, in this process of glycolysis, and even the Krebs cycle in the mitochondria. And one of them is NAD, okay, nicotinamide adenine dinucleotide, okay, NAD. NAD is an oxidizing agent. It's an oxidizing agent. So it oxidizes somebody, it oxidizes somebody, and then it becomes reduced, okay? Reduction is the gaining of electrons, okay? Reduction is the gaining of electrons. Oxidation is the loss of electrons. You need to know that. So what's happening here is that NAD is extracting electrons from a number of reactions here that we're going to see, and it's going to become reduced. So when you gain electrons, you become reduced. Okay, think about electrons being negatively charged. You're like, okay, I'm becoming reduced because I'm more negative, I mean, that's a way to remember, but it's not the actual thing that happens, okay? But gaining electrons makes you more energized, okay? So NAD will become NADH, and that H is going to have electrons, okay? So NADH will be a high energy intermediate, as a result of that. Okay, so let me continue on. Okay, now another word that you need to understand here: substrate levels phosphorylation. Substrate levels phosphorylation. When something is phosphorylized, when a phosphate is added to something, right, then it becomes phosphorylated. Okay, so when we're adding a phosphate to adenosine diphosphate, then we make adenosine triphosphate. Okay, so we're going to be making adenosine triphosphate by extracting a phosphate from somebody to make ATP. When we do that, that's called substrate level phosphorylation. We're getting a phosphate from a substrate to make ATP. Okay, so little energy is made through this process, okay? There is another process that is more significant that happens in the mitochondria, which is called oxidative phosphorylation. And through that process, we make a lot more ATP. All right, so let's look at glycolysis. In glycolysis, we have an energy investment phase. Okay, so here's glucose. So glucose was taken into the cell. Okay, glucose was taken into the cell, and we wanted to trap it in the cell. So we invest ATP. So we add a phosphate. Okay, we add a phosphate, and we add that phosphate at the 6 carbon, and now we have glucose 6-phosphate. So now glucose has been trapped in the cell. Okay. You know, so this is more like biochemistry. I'm not going to, you know, I'm not going to go through this. Notice that there is an isomerase here, and the reason for this enzyme to be there is just to add another phosphate here. The thing is that I want you to know in synthesis, okay, because if I go into like what these enzymes are doing, like, you know, a kinase will phosphorylate, right? You see here, a kinase here will phosphorylate again, add a phosphate again. So kinases add phosphates, okay? Isomerases move things around or rearrange things, you know? So I don't want to go into like what each enzymes do, because that's a topic of biochemistry, okay? But what we need to know is that in the beginning, we have an energy investment phase where 2 ATPs are invested, okay? And then we can see that we get to a certain step here in glycolysis where the molecule is going to be split into 2, and you're going to have, on one side, you're going to have a dihydroxy acetone phosphate, or DHAP, and you have glyceraldehyde 3-phosphate. What we want to do is like this one here, we want to convert it to this one. So we're going to have 2 of these. Okay, 2 molecules of glyceraldehyde 3-phosphate. We want this to move forward. Okay, if we go the other way, we might be building something else. Okay, all right, so let's keep going. And now we have an energy payoff phase, you know, meaning that we're making energy. Okay, notice that NAD is coming into the equation here. This is, again, an oxidizing agent. It's going to oxidize this substrate, and it's going to become reduced. Reduction is gaining of electrons, so this is a high energy intermediate, okay? So what we're going to do here, we're going to use the phosphates from this molecule. We're going to use one of the phosphates here. Remember that we have two of these molecules. So we have like 4 possible phosphates that we can use, right? So let's say we use 2 of them and we make 2 ATPs. So we use 1 phosphate and another phosphate, right? And we're adding it to ADP. So a phosphate added to ADP, adenosine diphosphate, we make adenosine triphosphate, okay? So we use another phosphate and we make another one. But remember, we have 2 of these molecules. So we have four phosphates available. So we can still make more ATP, okay? So here's you're making 2 more ATPs over here. Okay, you see there is a rearrangement here and so forth. But what we're making 2 more ATPs. These ATPs that we're making here is through substrate level phosphorylation. So we invested how many ATPs? 2 ATPs. How many do we made at the end? 4 ATPs. So we need to subtract from 4 the 2 that we invested in the beginning. So at the end, we're making 2 ATPs. Okay? And notice the end product here is going to be 2 molecules of pyruvate. Okay. So we have 2 molecules of pyruvate and 2 ATPs net. Okay? Because we made 4, but we have to subtract 2 from the beginning. So net, we have 2 ATPs, we have 2 molecules of pyruvate, and we have 2 NADHs that were made. So those are the end products of glycolysis. So what do we need to know? Well, we need to know that glycolysis is the breakdown of glucose, okay? And this is taking place in the cytoplasm, and we're making energy from it. we're making energy. We're making, we are also, converting. So we had one glucose molecule, we split it into two, right? And at the end, we got pyruvate, which is how many carbons are here? 1, 2, 3. So it's a 3-carbon sugar. It's a 2-carbon sugar, no. It's a 3-carbon molecule. 3-carbon molecule, okay? Pyruvate is a 3-carbon molecule. Remember, we started with glucose, which is a 6-carbon molecule. So we split it into two, and now we got 2 molecules that each have 3 carbons, okay? We call this pyruvate. Hey, we're done with glycolysis. Glycolysis is an anaerobic process. It does not require oxygen. It takes place in the cytoplasm, and we're making what from it? We're getting 2 NADHs. We're making, we're making 2 ATPs and 2 pyruvates, 2 molecules of pyruvate. That's it. Okay. Now, what happens if you did not have oxygen? So let's say that you're doing peak muscular activity, like you're lifting heavy weights. I just want to get big, like who cares if I'm breathing, Okay, so that's not the way. All right, so we're making, so if we do that, the energy that we're making is from glycolysis, okay? Now, also, if there is a respiratory condition that is compromising your gas exchange and you're not getting enough oxygen, again, you're stuck with glycolysis, okay? You cannot take pyruvate into the mitochondria if you don't have oxygen. Instead, pyruvate is going to be reduced into lactic acid or lactate, which I like to call lactate because lactic acid in aqueous solution is called lactate. Lactate is the ionized form of lactic acid. Okay, so look what happens. Just so you understand how important this is, okay? I want you to understand something here. This is critical for your, for when you're in the hospital. So here is, I want you to see this here. So glucose, right, is, through glycolysis, is broken down into pyruvate, okay? So glucose, the breakdown of glucose, which is called glycolysis, the end product will be pyruvate, right? Now, you're making 2 ATPs and you're generating NADH. But look what happens if you don't have oxygen. So somebody comes short of breath in the hospital, and you're like, and the cells are suffering because they're dying, they're getting damaged because they don't have enough oxygen to make enough ATP to run their processes. So we need to give them oxygen, we need to go give them oxygen to the patient. That's why they say airway, ABCs, airway, breathing, circulation, airway, oxygen is important. So, all right, so now, so let's say you're at this point, you get 2 molecules of pyruvate. I said, I want to make more ATP. I want to get into the mitochondria. But if you don't have oxygen, if you have heart failure, if you have COPD, if you have something that compromises your oxygen, your ability to get oxygen, and the cells are not getting oxygen, you cannot take this molecule into the mitochondria. Instead, it's going to be reduced into lactate. Who reduces it? NADH is a reducing agent. So the other way, NAD plus was an oxidizing agent. It oxidized glucose into pyruvate, basically, okay? And it became reduced. Now, this is a reducing agent. If you don't have oxygen, NADH is used to reduce pyruvate into lactate, okay? And lactate is another 3-carbon molecule here, okay? And this reaction requires an enzyme which is called lactate dehydrogenase. Lactate dehydrogenase, LDH. LDH is measured in these patients, that are short of breath. Lactic acid, is also measured. So if there is a high, if lactate is increased and LDH is increased, that is a confirmation that you need to be administered oxygen, that you need to administer oxygen to the patient. So we need to find ways, right, to confirm it so that we can build the insurance. The insurance will not pay if you don't show them reality. Anybody can come up into the hospital and say like, and they're just fine. You can. This is like something that you have to become aware. Okay, there's patients that do that. Okay, just to get in, and get seen more faster than other patients. They don't want to wait. But again, you have to confirm it. So you say, okay, oh, look at him. He's in a lot of distress here. So let me do a blood test. Let me check for LDH and lactic acid, lactate. If they're normal, man, he's like faking it. So, again, but notice that once oxygen becomes available, let's say the patient has COPD, or the patient has like a heart failure and is coming very short of breath to the hospital, and you give them oxygen, right? Now, lactate is going to go to the liver, and the liver, there's a cycle there that's called the Cori cycle. You learned that in AMP1. The Cori cycle, C-O-R-Y, Cori cycle. The Cori cycle will convert lactate into pyruvate again. Okay, so when oxygen is available, this reaction here is reversible. NAD you can go the other way. Okay, you can go the other way and make pyruvate again, or make glucose again. Okay, so again, how important it is, to understand that, because the number one cause of hospital visits is what? Shortness of breath. If you're short of breath, you're going to go to the hospital. You're going to go to the hospital. So number one cause of visit is shortness of breath. Okay? I'm not going to the hospital unless I'm short of breath. If I'm short of breath, oh, that's serious. I can't breathe. I need to get to the hospital. So shortness of breath. And why? Because they don't have enough oxygen to make ATP. Okay? So the cells is like, I need oxygen, right? So so you can have a better understanding of this. That's why we're going over metabolism. There is something else called alcohol fermentation. Okay, and this happens in, they say to a certain extent in our cells, but this is more associated with bacteria. Okay, so that's when in bacteria, pyruvate, bacteria, they use glucose too. So pyruvate, you decarboxylate, you remove a CO2. So you remove a CO2 and you make acetaldehyde. And acetaldehyde is reduced to ethanol. So like, for example, in my backyard, I have like cashew trees, and I made wine from cashews. And I use some, I used yeast. I use yeast to ferment, to create alcohol fermentation. So from glucose that you have in the fruit, we can make alcohol. And then we can put it in a dark room and we leave it there for years. And the longer it stays there, okay, and there is a process of distillation and all that stuff, that I did. The longer it's kept there, the more alcohol you'll make, okay? And so it's interesting, we can this is also used, yeast is also used in bread, in the baking industry, in the wine making industry, in the beer making industry. They use this here. My dad showed me how to do it. My dad learned it from his grandfather, and we made wine from different things, grapefruit, different things, and cashews, and we can make all sorts of wine, mango, anything. Okay. Anyway, this is something else. What does your body, what your body does to alcohol? When you drink alcohol, the liver, will there is ethanol here. Alcohol will be, there is something called like alcohol dehydrogenase, is an enzyme in the liver, and then it converts ethanol into acetaldehyde, and acetaldehyde, it's converted into acetic acid by acetaldehyde dehydrogenase. So notice that we're making NADHs. We can use energy. We can from alcohol we can generate ATP as well. But again, stay away from alcohol. Okay, that will give you liver cirrhosis. All right, so let's. There's a lot of implications with alcohol. Drinking alcohol will make your antibiotics and opioids less effective. So there's a lot of things about that. So stay away from drugs. They're not good. All right. Now let's think about something else here. So let's say that that oxygen is available. Let's say that oxygen is available. Okay. So you're giving oxygen, therapy, and now you have oxygen. Now your lactic acid levels are going to drop. Your LDH levels are going to drop. LDH is lactose dehydrogenase. That's going to drop, right? And then you're getting pyruvate once again. And pyruvate has to be taken into the mitochondria. By the way, one time I was in the hospital. A relative of mine was there, and I asked them, you're running this test, LDH. I knew what it was, but I asked the technician, what is that for? And he says, I don't know. The doctor ordered it. I'm like, how can you be working and doing things and not be investigating what these things are? I think it's always have an interest of what you're doing. Okay, so you become aware and you learn. Okay, so he didn't know. Okay, so now we get 2 pyruvates, but for simplicity, we're using one molecule pyruvate here. Notice that it gets transported, into the mitochondrion. Okay, this is the matrix of the mitochondrion, and here's the outer membrane, here's the inner membrane, and here's the intermembrane space. Here they're showing you that is a protein here, a transport protein helping pyruvate to get into the cell. This is the 3-carbon molecule, remember? 1, 2, 3. But out here, we also have another transport protein. We have one in the outer membrane. We have one in the inner membrane. These proteins are made from DNA. Like DNA, protein synthesis, right? You express genes, and you get and you make proteins, right? And these proteins might serve a function of transporting down something. So imagine there was a mutation in the gene and you couldn't make this transport protein. Oh my God, you're screwed, because you're not, how are you going to get this in and get energy, right? So you can see how important this is. That will be very rare, by the way. Probably to not survive. Okay, but let's say pyruvate gets transported into the matrix of the mitochondrion, right? We're going to remove CO2 from it. Okay, we're going to remove CO2 from it. We're going to use NAD. Okay, so you know that pyruvate is getting what? Oxidized into acetyl-CoA. So we're generating NADH, right? And we have coenzyme A. We need coenzyme A. There is a lot of things that are happening here. This reminds me of medical school when everything that participated in this enzymatic reaction here was summarized by this mnemonic: tender loving care for Nancy. Yeah, a lot of things that are needed here that are required for this process. It's not, this is just keeping it simple. But notice that we're getting acetyl-CoA. Okay, 1 pyruvate, 1 acetyl-CoA. But remember, we have 2 pyruvates. So we're going to get 2 acetyl-CoAs. Now, acetyl-CoA is a 2-carbon molecule. Look at that, 2-carbon molecule. Glucose is a 6-carbon molecule. Pyruvate is a 3-carbon molecule. And now we're getting a 2-carbon molecule. You got to be observant, You got to be observant of what's happening here. All right, now let's move on. Acetyl-CoA, what's going to happen with acetyl-CoA? Okay, I have a lot of structures here. Don't worry about it. It's just to help you understand something else, but you need time for this, But here's what they call the citric acid cycle. The citric acid cycle, or the Krebs cycle, or the tricarboxylic acid cycle. Okay, there are different names, but the most common name is the Krebs cycle. But you need to know that it's also called the citric acid cycle because they use that in exams. They call it citric acid cycle or Krebs cycle. Here's acetyl-CoA. Notice that acetyl-CoA combines with oxaloacetate. and you're going to make citrate. And then from citrate, you're going to make isocitrate. And from isocitrate, you're going to make alpha ketoglutarate. And from alpha ketoglutarate, you're going to make succinyl-CoA. From succinyl-CoA, you're going to get succinate. From succinate, you're going to get fumarate. From fumarate, you're going to get malate. From malate, you get oxaloacetate. You see, it's a cycle. It's a cycle. This is called the Krebs cycle or citric acid cycle. During that process, what is happening? Okay, what is happening? You're generating CO2, right? So 2 molecules of CO2, another 2 molecules of CO2. Because remember, these are like 2, these are double. Everything is doubled here. So you're generating CO2. You're generating NADHs. You're generating FADHs. And you're also generating ATP through substrate level phosphorylation. You see it here. 2 ATP molecules are made in the Krebs cycle. Okay. We have 2, and 2 is 4, and 2 is 6. So we're making 6 molecules of NADH and 2 molecules of FADH. Remember that everything is by 2. Okay, you have to double everything. Wherever you see something is going to be doubled. So you see 1, 2, and 3. 3 times 2, 6. 1, but it's double. 1 times 2 is 2. 1 ATP is double. So 2 ATPs. Okay? So 6 NADHs, 2 FADHs, and 2 ATPs. That's what we're generating in the Krebs cycle, which is happening where? In the mitochondrial matrix. Okay? And we need oxygen to be in the mitochondria, right? There is other shuttles here. I mean, I'm not going to talk about the shuttles. This is more like biochemistry. So, so let's see, like here, you see here, this is something that you learn in biochemistry. You learn about the citrate shuttle, the malate shuttle, like these shuttles, okay? I never understood what a shuttle was until like I got to the airport and said, like, you want to take a shuttle? I'm like, oh, a shuttle bus? Okay. Back then when I was a student, I didn't know what that was. The professor didn't explain. Okay, so I just wanted you to see where all of these high energy intermediates are heading. NADHs, FADHs, all of those are heading into the electron transport system. Okay, the electron transport system takes place in the inner mitochondrial membrane. In the inner mitochondrial membrane. Okay, so then and so the inner mitochondrial membrane. Okay, so I'm getting a little bit distracted here. The kids are making noise, and I'm just signaling that keep it down, keep it down. I'm live here. Okay. So in the inner mitochondrial membrane, we have something called the electron transport system. Okay. So where are these NADHs, FADHs heading to? The electron transport system. Okay. So let's see what's happening there. Let's see what's happening in this electron transport system. It's a lot of material, but I need to summarize it, right? In the electron transport system, also known as the respiratory chain, look at that. Oxygen is coming into the equation here. It's a sequence of proteins known as cytochromes. Each cytochrome has 2 components. Has a protein embedded in the inner membrane of the mitochondrion. It has a pigment complex that surrounds the protein. And this pigment contains a metal ion known as iron or copper. So we need iron and copper here. All right. Now iron will make it red. Copper will make it blue. Okay. So we have all of these proteins embedded in the inner mitochondrial membrane, and they have a pigment complex that contains either iron or copper. Okay, so the NADHs are arriving there and the FADHs are arriving there. And we need to know who's receiving this. Okay, NADH is being received by flavin mononucleotide. I'm not going to ask you about FMN. Okay, FADH2 proceeds directly to coenzyme Q or CoQ or ubiquitin. I'm not going to ask you who's receiving it, okay? But what happens is that when these high energy intermediates arrive there, they're going to be stripped from the electrons. The electrons are going to be stripped from them. And the hydrogen atoms, right? The hydrogen atom has an electron, right? So the hydrogen will be on its own without an electron. A hydrogen without an electron is called a hydrogen ion or a proton. A hydrogen ion or proton. What is going to be the fate for that? What is going to be the fate for that? Those hydrogen ions are going to accumulate. They're going to be pumped. There's going to be pumps in here in the inner membrane. They're going to be pumped into the intermembrane space, those hydrogen ions without their electrons. And the electrons are going to be passed on from one embedded protein in the inner membrane here, from one to the other, to the other, to the other. So that means that if I gain an electron, I become reduced. If I pass on the electron, I reduce somebody, but I become oxidized. So we're going to have these reactions here like redox, reduction, oxidation, reduction, oxidation, reduction, oxidation. At the end, these electrons are going to be received by oxygen, the respiratory chain, right? So oxygen are going to receive these electrons. But what's happening with these hydrogen ions here? These hydrogen ions here are accumulating, and they're creating a concentration gradient there, which they're creating potential energy that can be transformed from one form to another, for movement. So these hydrogen ions are going to be moving from high to low. They're going to be moving across here through these ATP synthase. Remember the FO and the F1 regions of these ATP synthase that we talked about in the beginning. This is the FO region here. This is the F1 region here. So this one here is hydrophilic, right? Hydrophilic. Okay. So now these hydrogen ions are coming in back into the matrix. And when they do that, they're running this ATP synthase. And what is it doing? They're adding, phosphates are being added to ADP, and you're making ATP. This is called oxidative phosphorylation. Oxidative phosphorylation. And it's coupled with the electron transport system here. So how is it coupled? Because it's dependent on it. And look at this here. Hydrogen ions come back in here into the matrix, and then hydrogen ions are going to combine with the electrons, and that is going to, and then oxygen is going to be gaining this, so it's going to be reduced. So oxygen is reduced to water. Oxygen is being reduced to water here. So we're making water. So let's sum this up, okay? And by the way, these NADHs here, notice how they leave. They leave naked. NADH leaves as NAD plus. FADH is going to leave, FADH2 is going to leave as FAD. So it's going to be lived, like it's going to leave. If you go here, look at this here. Let's go back a little bit here so you can see something. You see here, FAD. So FAD and NAD, they're generated again, right? And they're going to go back there again to extract electrons and remove hydrogens, right? So that's what they do. NAD and FAD, they'll just get electrons, right? So that they can take them to the electron transport system so that we can generate hydrogen ions so that we can make ATP, right? And water. But we need oxygen, right? We need oxygen in that respiratory chain, right? We need oxygen. So that's how that works. Okay. Now, another thing that I want you to know, how many ATP molecules can be generated from one NADH. from one NADH. Okay, so from one NADH, that will give you what? One NADH gives you 3 ATPs. Is it 3 ATPs? Yeah. See here. Somewhere in here, we have that. Hold on. Da-da-da-da. Give me 1 second. I need you to understand this here. It says here, one NADH gives you 3 ATPs. In reality, they gives you like 2.5, but we always round things off, right? So one NADH gives you 3 ATPs. And one FADH2 gives you 2 ATPs. In reality, it's 1.5, but we're rounding things off, okay? We have to do that for the exam. So for the exam, you need to know that one NADH gives you 3 ATPs, and one FADH2 gives you 2 ATPs. You have to know that. Because if I tell you how many ATP molecules are made from 8 NADHs, you're like, oh, 8 times 3. And then you'll calculate that. How is your math? How is your math? Okay. So here's a sum of carbohydrate metabolism here. Glycolysis in the cytoplasm takes place in the cytoplasm. No oxygen required. It's an anaerobic process. You're investing 2 ATPs in the beginning. You're generating 4 ATPs at the end. Net, you have to subtract these numbers. So net, you make 2 ATPs. You're also making 2 NADHs and 2 pyruvates, 2 molecules of pyruvate. Those are the end products of glycolysis. 2 ATPs, 2 NADHs, so 2 ATP molecules, 2 NADH molecules, and 2 molecules of pyruvate. All right, now you have oxygen available, you take pyruvate into the mitochondrial matrix. And then from pyruvate, you're gonna make acetyl-CoA. Okay, acetyl-CoA goes into the Krebs cycle, you generate NADHs. Notice that from converting from this oxidative process here of pyruvate into acetyl-CoA, you're generating two CO2 molecules here and 2 NADHs as well, okay? So keep that in mind. So CO2 is made in the mitochondria, right? CO2 is made in the mitochondria, and then it comes out, it diffuses out. Remember, in AMP1, the chemistry chapter, okay, you learned that carbon dioxide was a non-polar molecule. Non-polar molecules, they diffuse through the phospholipid bilayer, okay? Through the phospholipid bilayer. So CO2 diffuses through the phospholipid bilayer, and then it goes into the blood, right? And it's going to be taken by hemoglobin in the red blood cell, and it's going to be transported to the lungs, right? For elimination, because it's a waste product, okay? Now, the NADHs, they're going to go into the electron transport system, and you know what happens there. This is the respiratory chain, right? And then you're going to be stripped of the electrons. The hydrogen ions are needed to make ATP later on to run the ATP synthase, which is an enzyme, a protein that is embedded in the inner membranes, inner mitochondrial membrane. And that's how that works. And we call that, when ATP synthase is adding phosphate to ADP, that's called, that is called oxidative phosphorylation, and is coupled with the electron transport system. So look over here. So those NADHs from glycolysis, they get into the mitochondria, right? We said that we make how many ATPs from it. So we have 2 NADHs, and we make 3 ATPs from 1 NADH. So we have to multiply 2 times 3, right? That's 6. But notice that we're getting only 4. That means that there was some type of investment here. Okay, so from the NADHs, from glycolysis, we generate 2 ATPs. Notice how important it is oxygen. Oxygen allows us to take this pyruvate into the mitochondria and make a lot of energy. And NADH, instead of using it to reduce pyruvate into lactic acid, if we didn't have oxygen, now we're taking it into the mitochondria and we're generating more energy, right? So you can see that 2 NADHs from converting pyruvic acid or pyruvate to acetyl-CoA. So 2, and then 6 NADHs from the Krebs cycle. That is 6, 7, 8. That's 8 of them. So 8 times 3 is 24. Okay, FADHs, how many? 2 FADHs. So from FADH, we can get 2 ATPs. So 2 times 2 is 4. And then we have 2 ATPs that were generated through substrate level phosphorylation in the Krebs cycle. That goes there as well for the summation, right? And look how many ATPs we get. If we had oxygen from one glucose molecule, we can generate up to 30. It says here, what, 36? 36 ATPs. Look at that. If we didn't have oxygen, we can only make 2 ATPs. But if we had oxygen, we make 36. Sometimes they say 36 to 38 ATPs. That's a lot more ATP that we can use to run all the processes or repair. You know, if something is needs to be repaired, we need ATP. You know, when people get like a respiratory illness and they're like so tired, you know, it says like, you need to rest. You need to rest so that you don't use energy for other things. The time now is to rest so that you can repair all this damage that is being caused by this respiratory virus, okay? They say that viruses are the biggest oxidizing agents, meaning that they destroy cell membranes, and we need to repair them. So we need energy. We need to conserve energy. We need to rest. We need to breathe. We need to breathe so we can make a lot of ATP, okay? So that it can help us repair things in our body. So I hope that you like this presentation, okay? And you can have a better understanding of carbohydrate metabolism, okay? There's other things here that I talked about, like gluconeogenesis, making ATP from other sources that are not sugar, okay? There's a number of sources here. I told you that in the review, okay? I don't want to make this more extensive than what it is, okay? I want you to know that gluconeogenesis is making glucose from other sources that are not glucose, okay? And this usually takes place when you have, you know, when you're fasting, okay? When you don't have glucose available, and you're fasting, you don't have glucose available. If you don't have glucose available, you have to make it from other sources. And that's what that is. I just want you to know that gluconeogenesis is making glucose from other non-carbohydrate substrates. The most common is lactate. Lactate is the most common non-carbohydrate source. Okay, so I don't want to, again, like I don't want to extend that. That will be another topic. I don't want you to lose focus in everything I mentioned from carbohydrate metabolism, you know. And again, also when you're fasting, you're breaking down glycogen, the storage form of glucose. That's called glycogenolysis. And we talked about that in the past in AMP1 when you were doing moderate muscular activity or peak muscular activity. Okay. And then if we are, you know, if we're not fasting and we're eating, we are storing glycogen. We're storing glucose in the form of glycogen. That's called glycogenesis. Glycogenesis, you know, making glycogen from glucose. And we'll stop here, and I'm going to make another video of lipid metabolism and then a third video on protein metabolism. Okay, so I'll stop here.